Okay, so for the benefit of those listening, this is I'm David, and this is my how to study for stats thing. And if Gary, you're listening too, I apologise, and I hope you're not offended. But I'm not trying to teach them stats. I'm trying to give them some advice on how to study for it. So please don't be offended, Gary. I still want to be your friend. Okay. Right, so what happened is a few people have been in the Maths Learning Centre and they've said, we just need some more advice on how to go about studying this and how go about dealing with it in the exam, mainly because Gary said there's only going to be technically four stats questions in the exam. So if you happen to not study something, of course it's going to be the thing that's in the exam. So you need a way of trying to deal with all of it at once so that you make sure you cover everything. And so that if you do get a question that you're not familiar with, you'll be able to deal with it anyway. So that's the idea. And what I've done is someone very friendly has allowed me to borrow their notes from Eng Maths 1. And I'm going to try and make sure I match with what Gary said because everyone teaches statistics slightly differently. So if something I say does not match with what you were told, please let me know. I'm just doing it as it would have been done, say, in medicine or vet science or something. So if I say something about stats that is not what Gary said, please stop me and say, Gary didn't say that, and we can fix it, okay? Right. So firstly, this is your formula sheet for your exam. And on the other side, which I haven't photocopied, there'd be stuff for differential equations as well. But I'm going to let you guys deal with that on your own. This is the stats side, and there's some important things that are missing from this that you have been told that you need to remember anyway, right? Because it hasn't got on here the MATLAB code that goes with these things. And Gary specifically said that he's going to either get you to interpret what MATLAB code is doing or possibly to write a MATLAB code that would produce a certain response. So it would be worthwhile for you while you're studying possibly to write on this piece of paper or nearby the MATLAB code that goes with various things. All right? So that's a piece of advice now. Okay, so I'm going to take a vote. Well, I'll just ask for a response from the floor. What do you want me to start with? Anyone? What do you want me to start with? There's like 4 or 6 things in stats. So maybe, I don't know, the different types of distribution and when they come up, maybe? Regression. Regression? Cool. I shall start with regression then. Okay. In order to start with regression, I'm probably going to have to talk about some other stuff first. But you'll see on your formula sheet that these 3 here belong to regression. You've got regression slope, regression confidence intervals, and regression prediction intervals. So just have a look in your notes to see what Gary said before I go on to that. So we've got basic probability, covariance. So this is where it starts, right? Okay. So what is it about regression that bothers you? Just not sure what it's about, or?
Regression and MATLAB code, I suppose.
Massive
block of code.
Massive block of code, and what is it doing?
We're given like the big block code, and then we have to answer a series of questions.
Ah, so that's this thing that was in this thing that I have here. I'll see if I can zoom in on it enough for you to see it. You can see that I had like last night to prepare for this, and basically didn't. So, okay, so this sort of thing, that thing.
Yeah.
All right. I'm just going to read this. So we've got reg stats, cost depth, variables have been created in the current workspace. We've got a scatter, theta. Yay. Wow. Gosh, I hate MATLAB. One of the reasons I didn't do engineering is because I hated MATLAB. And also I didn't like differential equations. But the only way to avoid any maths is to do all the rest of maths, so I did pure and stats. Cool, okay. So you need to know which bits of these are referring to which bits of the regression course, and that's something that we want to draw on this piece of paper if we can. So let's see. My picture of regression that's in my head, that I'll do off the top of my head and see if it matches with what Gary thinks in a minute, goes like this. It goes, you've got relationship between a couple of variables, maybe something like this. And you've got an x and a y of some sort. And you can draw a scatter plot to represent how they're related to each other. And hopefully you want it to be this lovely straight line where you can put this awesome line of best fit in. Okay. But the problem can happen when it's not actually linear. It might be curved instead. So scatter plots can look all different ways. So there might be something that's a lot more, like that, which is curved. And there's going to have to be methods for dealing with that, which Gary has hopefully mentioned to you. No. Well, he's mentioned it, but not actually what to do. Okay, cool. So, linear regression that you've been taught about specifically deals with this situation where it's not curved. Okay? If it is curved, then you have to do some sort of other thing like do logs or something like that to find a better formula that works here rather than a straight line. But you've been told about linear regression, which is where the straight line seems appropriate. And the maths that goes behind it is basically trying to find what this line is based on these dots here. And so it's actually a differential equation that you solve to find what this line has to be. Because what you want is all of the distances of the points to that line to be minimized as minimized. So you get find the total distance, you differentiate it, and you figure out what x's give the minimum, and that is the answer. Now you don't have to do any of that, but just so you know that that's what's going on in the background. And there's this complex formula that produces the slope and the intercept for that line. That's a plus. Something like that. Okay? And so this beta naught is the intercept over here. Beta naught. And the beta 1 is the slope. And for regression, it's the slope that's the most important thing that you want to know about, because it's the slope that tells you how one thing changes with the other. The intercept's less relevant. And it's the slope that tells you whether the relationship exists at all. Okay? Cool. And so what the linear regression will do is it will tell you what all of those things are, and it will give you a whole lot of hypothesis tests as well to tell you whether they ought to be 0 or not. Okay? Let's go back and have a look at that other question now. All right, so we've got this question that has output and also some questions to go with it. And let's read what it says, and I'll talk through it, and I'll try and say what my interpretation of how regression works is, and then if it's slightly different to Gary's, then that might mean that it works for you a bit better this time. Okay, so let's have a look at this. This is the actual question in the exam that he was referring to. So the following questions refer to the linear regression model y I think, is beta naught plus beta 1 xi plus ei. And that ei is the error. It's how far that the line is from the real value. Okay, I'm going to write this out down again in a second. It says identify the predictor and response variables in the present context. Did he say what the context was? Yes, he did. The depth in thousands of feet and total cost in thousands of dollars were recorded for each of 16 offshore wells located in the Philippines. Shown below is a scatter plot and a transcript of the MATLAB analysis. So there's the scatter plot, and it looks roughly linear. We can probably draw this awesome straight line on that, and that would be about right. And we want to find out whether there's really a relationship between depth and cost and what that relationship actually is. So when we read the question, it says, identify the predictor and response variables. Okay, so it looks like we're attempting to find out what the cost is if you know the depth. That makes sense. If you're going to drill the depth of an oil well, you'd like to know how much it costs beforehand. So the predictor would be the depth, and the what did he call it? Response variable is the cost. Now, usually it works in the case of causation. You know, the well being deeper causes the well to be more expensive, but sometimes it doesn't always go that way round. It might be, for example, not for you guys because you won't be doing this, but you know that as a tree gets older, it gets wider. But in order to find out how old a tree is, you have to cut it down. So even though age causes the width of a tree to change, it may be that you want to measure the width and use that to figure out what the age is. So even though age is the really thing that causes the other to change, your regression can be the other way around because of what you're attempting to do. So if what you're attempting to do is use some things to calculate another, the outcome, that's the response, and the things you're using to calculate it, that's the predictor one, okay? So that's all good, blah, blah, blah. Okay. So regression requires you to make assumptions because it's based on some fairly heavy-duty maths, and the maths is only going to work properly if your data is arranged in the right way. So in order to calculate that line of best fit, you don't really need any assumptions at all, just to find what that line is. But if you want to use it to predict values of things with any great accuracy, and if you want to be allowed to do any of the hypothesis tests that go along with it, you have to assume that at least one of the, that the residuals, the differences from the line to that, are normal. So when we look at these other plots that he gave us, this is the normal probability plot. That's telling me whether that normal distribution assumption is appropriate, and it doesn't look too bad. They're all quite close to the line. Okay, so in statistics, if you get a normal probability plot for any distribution, it's telling you, comparing what your thing is to what it ought to be if it was from a normal distribution, and it'll line up that way. Okay, cool. And then this one is the residual plot, and that's just making sure you've got some sort of even scatter going on, because if it was getting narrower or if it was getting wider, that would be bad. So now that I know exactly what he's doing, I can actually talk through all of that in the right direction. Consider the hypothesis. Okay, let's go for it. I've now got it. I am making this up as I go along, and I'm sorry if that's the case, but remember that I never actually did engineering maths, so you've got to give me a chance to and the course has changed like every year for the last 5 years, so you've got to give me a chance to make it up as I go along. So regression's trying to find that formula, remember? And there's several parts to it. We find the formula, and we'll get output, and it will tell us what the formula is. So we'll see in this output here, this is the least important part, but it is the part that will get you at least 1 mark in the exam. Okay, so where is it? We need to find where the betas are. Does anyone know where they are in that picture? I don't know what MATLAB's doing. Where's the beta 0 and where's the beta 1? Or is it in this picture? Wow, that's a bad picture. Is that what MATLAB does when you type in code? Who knows? Where's the beta? Does anyone know?
First two of the answer.
Which answer?
The T-stat beta.
Those two or those two?
The first two.
Those two? Those two there? And which one is which? The first one's beta 0 and the second one's beta 1? Yay, okay. That's what you need to know. You see, I didn't know, so I would have failed your exam. But I would have been able to answer the other, I would have been able to generally talk about it, but it's the MATLAB code that's the important bit. So it looks like that when you do this, this reg stats, that's telling you to put the input variable and the output variable, no, the output variable and the input variable in that order, because remember the cost was the thing that we're trying to predict, and we've got, that's telling us to do the scatter plot of the residuals, and that's telling us to do the normal plot. Okay? And this is telling us we want the betas, we want the standard errors, we want the t-statistics, and we want the p-values. So this is the betas, this is the standard errors, and this is the t-statistic, which is actually that divided by that produces this answer. And that's the p-value. Okay, so this p-value is testing, this p-value is testing the hypothesis that this number ought to be 0 in that formula. So remember, I'm going to say this several times in a minute, hypothesis tests tell you whether things are equal, whether things have relationships, whether things are 0, that sort of thing. So we would like there to be a relationship, but we have to assume, according to the maths, that there is no relationship, because mathematically there's only one way to have no relationship, but there are infinitely many ways to have a relationship. So this is the beta 1, and we would like that to know if that is supposed to be 0. It's actually 1 times 10 to the 3, so we'd like to think it's not 0, but the p-value will tell us that. So the null hypothesis is that this is 0, and the p-value says is shockingly low, so we conclude that it's not 0 after all. Because this is saying the chances of getting data that is as close to a straight line as mine, assuming that in truth for all oil wells it's not supposed to be on a straight line, is this chances, which is times 10 to the minus 8. Okay? So when Gary asks this question here of consider the hypothesis beta 1 is 0, state the values of the t-statistic and the corresponding p-value, should it be rejected? Well, we can do that. The t-statistic is here, and the p-value is here, and we should reject because that is below 0.05. And what we conclude there is that yes, there is a significant relationship here. Because if the p-value had come up as big, that would have said that 0 is one of the possibilities in that formula. So when we get our formula like this one just here, that would tell me that that beta 1 is supposed to be 0, which means that x isn't even in the formula, so there's no relationship. Okay? That's what that's talking about. Awesome. Right. So, as far as I know, you don't need to know the formula for actually calculating what the slope and the regression and the intercept actually are. Did Gary say that to you? You don't know? Did he even tell you in your book? Wow, he did. Oh, well, look, he even did the derivative thing. Look, there's our derivatives. Need to find it. Wow, he did a whole heap of stuff. But it appears what he really prefers is for you to interpret what MATLAB tells you rather than be able to calculate those things by hand, because that's just not worth the pain. So, however, he might ask you to do the prediction intervals and confidence intervals. So, what can happen is that this formula is awesome. It tells you what's on the line, right? But what it does not tell you is what all the possible costs are for your oil well. Okay? Because this line is not the same as what's on all these other dots. So it just tells you on average for oil wells of that depth what the cost is probably most likely to be, but it doesn't tell you what all the possibilities are for what the oil well cost is. And there are two intervals that will tell you that. You have this thing called a confidence interval. Okay? And what that tells you is it's telling you what the possibilities are for the average at a particular x. So at a particular x, which your lecturer has called x0. So at a particular x0, we want to know what the average y is supposed to be. Find the average y, okay? The formula tells you what you should do. You should just sub in x0 into the formula, like the beta 0 plus beta 1x, And that would tell you what the average y is. But the thing is that if you collected different data, you would get a different answer. And so what you want to do is you want to cover all of those possibilities. So you make this 95 or 98 or whatever % confidence interval that will produce what all the possible means could have been that produced your data. And so you get this formula here. Formula here, the regression CI, that says that you should get this middle number. Okay, this parameter here is the y, right? This is the y hat, it's the predicted y. You get this and go plus or minus this, and that will produce the answer. Now, MATLAB can actually do that for you, but since he's given you the formula, I assume he wants you to know how it works. Okay, so in this situation, I would actually get my x naught and sub it into the formula. All right, that's the first step. And that gives you the center. That gives you y hat, that's the center. Technically, these are the ones you get from your formula. So back there with my minus 2 times 10 to the whatever and my 1 times 10 to the whatever, they were the numbers that I put in these spots. And then what I'm going to do is I'm going to get this standard error formula, and I'm going to figure out what the upper limit and the bottom limit is. So I'm going to get the standard error. So I get the standard error from my regression, and I times it by all of this crap. SXX. Now that's from my formula sheet. And then I get these two answers and I go this plus or minus that. So y hat plus or minus the standard error. And that gives me my confidence interval. And that's saying that if x is whatever x0 is, I expect on average that the average oil depth is between the plus and the minus version. So in your MATLAB code, let's see where that is. Okay, so look what's happened here. x0 is 10, and we've asked MATLAB to get the beta 1, the beta 0, which is this one, and the beta 1, which is this one, and times it by x0. So what he's done there is he's subbed x0 into the formula beta 0 plus beta 1x. Okay? So you could, if you wanted to, actually type in the actual numbers and do minus 2.277 times 10 to the 3 plus 1.033 times 10 to the 3 times 10. You could ask it to do that yourself, but what he's done is he's tried to make it look harder to see using the MATLAB. Okay, so this is the bit where he subbed it in, and this here is the bit where he has found the top end of the confidence interval, because you've seen that he's got this. Oh crap. This here has got a T star. All right. Because you can read it off this thing, and he's reminded you how to do it. He's got the T star is here. Because what he's done is he's found, see that 0.975? If I'm making a 95% confidence interval, that's 2.5% on either side. There's 95 in the middle. There's 2.5% here. And there's 2.5% here. So I want this point here to have 95.97.5% below it. That's why he's used this 0.975. And the square root of the mean square error times all of this, he's just copied that formula from the regression confidence interval formula in the formula sheet and just subbed it in. And it appears that, oh, here it is. There's SXX. It's the sum of the depth minus the mean squared. So he's actually figured out SXX here, and he's subbed it into this formula here. So what he's found is the confidence interval for the mean, and the confidence in, and this is that's the confidence interval for the mean there. So you can see that this is my t star times the standard error, and this is a t star times a different standard error. And this one is the one for the prediction interval, because it's got a 1 plus 1 on n. And this one is the one for the confidence interval, because it's just the 1 on n. So he's asking you to read the MATLAB code and notice what has happened in that calculation and match it to what's in this statistical inference thing. Because here, see how this formula has a straight 1 on n and this formula just has a 1? Sorry? Did I? Oh, crap. Ah, you're right. This is the wrong one. Okay. You're good. See, this is good study. We get people to tell us what we're doing wrong. You should always study together. So here, that one is the 1 on n. It doesn't have the 1, so it's the confidence interval. That's got the 1, that's the prediction interval. And so if you look down here, he's used m1 here. That must be the prediction interval, because it's the one with the 1. That's the prediction interval there. And this one's used the m2. That's the confidence interval there. Now, you have to find that out for yourself. So you refer to what's written here and the other sheet, and you can figure out what's been done. Okay? Cool. So what this is saying, that since this is a confidence interval, that's saying that the mean mean cost at a depth of 10 is between this many and this many $100 million. And the mean, all right, that's the mean. The confidence interval tells you what the average is for that one. The prediction interval tells you what all the possibilities are. 95% of all the possible costs are between here and here. Okay, so this is what it will be on average. This is what it will be. Okay, because if the average is between here and here, then the actual values might be a bit more than the average, and they might be a bit lower than the average as well. So we've gone this one and we've gone down a bit to get that one, and this one we've gone up a bit to get that one. So even if you don't know how the formula works, you can know which one's the prediction interval because it's wider. Because this one is only covering all the possible averages. This is actually covering all the possible, well, 95% of the possible averages. This is covering 95% of the possible values. So if you want to cover all the values, you're going to have to cover more than you will if you just want to cover the average. So even ignoring all of this, this looks like a prediction. It looks like an interval, and this one must be the prediction, and this one must be the confidence. Cool. And that's because there's two philosophies. You want to know what it is on average, but if you really want to know about what the cost is going to be, you want to know an upper limit for what the cost is actually going to be. So you want to predict what the cost actually will be. And that's why it's a prediction interval there. Right. Now, hopefully that wasn't too confusing. I'm going to launch into some distribution stuff because someone specifically asked me about that yesterday. And I wanted to show you how that's done. And that's the stuff that I know the best. Yep.
I've seen a question a fair few times, the residual plot, the covariance, and the average. Like, what's the connection between
Residual
those?
plot, covariance, and...
Like linearity?
Oh, linearity. Okay. So in order to... I'm going to write those assumptions down. In order to do linear regression, there are 3 assumptions. Assumption. Oh, that's really unclear. You want it to be linear. So linearity means that the model, the picture looks linear. Okay? So something like that would be yes, but something like this would be no. And you can get that much better from the residual plot because it may look to you from this distance that they both look linear, but you want to zoom in a bit better than that. And so what you do is you put the line of best fit in and you subtract the line of best fit so that you get just the residuals. So what we can actually do that from is the residual plot. And so your residual plot will look more like this. And that's where the line of best fit is, flat across the middle. Because what you've done is you've taken the line of best fit from this one and you've subtracted the line itself. So you've actually just found this plot is just telling you how far everything is from the line. And to be linear, you want there to be no pattern here. So that's good because there's no pattern. Whereas something like this would be bad. Because there's a pattern. So if Gary said, from a plot, tell me if the linear assumption is appropriate, you would go, the residual plot has a pattern, a clear pattern, so there is linear assumption is not appropriate. Okay? That's when you'd have to do some sort of transformation. There's another assumption. So assumption number 2. All right, and there's no particular nice thing that does that. Assumption number 2 is the homoscedasticity. Did he say that word to you? Good. Some people just say constant spread rather than homoscedasticity, but you know, statisticians are proud of being able to say that word. So homoscedasticity means constant spread. Homo meaning same, and scedastic meaning to do with spread. Okay, so that means that on that residual plot you want constant spread all the way along. So you want something like so this would be okay. That's okay because it's constant spread. But something like this that gets wider as you go along, something like that, that's bad because that's not constant spread. Now sometimes it's hard to tell if you've only got a small amount of data and you're just going to have to go, it's not too bad. As long as you actually say the words, I'm quite sure that Gary will pay it out. So pay the marks as opposed to paying out. So if you notice that there's a region where it's much more spread out than another spot, then it's not homoscedastic. Okay. Now, and this however does say that a linear model is probably okay, because it's still evenly scattered on both sides of the line. There's no particular pattern as to what side it's on, but there is a pattern as to how wide it is. So that pattern in the previous one is actually a pattern as to what side the points are on, as opposed to how far away they are. Okay, and then the third one is normality. Oh, there's also the assumption that everything's independent as well, but you can't check that. So there's also the assumption of normality, which is saying that if you take these measurements from here and put them all in one graph of their own, just as raw measurements, they should be from a normal distribution. So that comes from the normal plot. The normal probability plot, and you want it to look roughly linear. So something like this is all right. That's okay, roughly linear. The further from normal it gets, the more like an S it will look. Bad, not linear. So roughly on a straight line. Roughly on the line, not on the line. Okay, it's distinct curvature there indicates it's not normal. Because this chart's telling you how far away from where it ought to be if it was a normal distribution. So if it was a normal distribution, you kind of say, well, this one's like above 70% of things. It should be roughly here in a normal distribution. And so you compare where it is actually in your distribution to where it ought to be in a normal distribution. And the curve might go the other way as well. But if it has distinct curvature or there's wiggly bits, it's not normal. That's what you would do. Okay. And that's what makes regression so hard, because there's the regression itself, which is the reading the MATLAB, and then there's this other airy-fairy bit, which is from the plots. Okay. And you'll notice that even though we go to all this great effort to have all these wonderful hard down the line hypothesis tests which give a p-value to 17 decimal places, and then we check the assumptions and it's all just stare at the graph and say, oh, that's all right. It just doesn't seem to match, but that's just the way statisticians do things. So the assumptions, and they don't have to be exactly okay, and that's why you can just look at a picture and go, oh yeah, that's fine. But the hypothesis test, you've got this nice raw number with the p-value that gets everything pretty. So just note that if you're doing the actual analysis, you want to be accurate, but if you're just checking if the analysis is okay, you can just stare at the pictures and say that's roughly okay. All right. So, doing well. So one thing I would add before I move on to your mental cheat sheet, you can't take a real cheat sheet in, but you can know what to add to this. You can say that this one is wider. The prediction interval is wider. That's just a useful thing to remember to yourself, because that's much easier than looking at the formula that was used to calculate it. Okay? Okay. And you can also say that this regression slope is testing the null hypothesis that there is no relationship. Okay? That's the same thing. So that p-value that belongs to the beta 1 that was here, this p-value here that belonged to the slope, that's telling you whether there's a relationship or not. Okay? So if he ever is a bit less distinct about it and doesn't say h0 beta 1 equals 0 and just says test the hypothesis that there's a relationship, that's the same question. Okay. So let's start having a chat about these. Because these are a different story, really. Because there's several things that you might use statistics for as an engineer, and one of them is to try and answer questions such as, is there a relationship between these things? Or what is the formula that relates this to that? That's really useful, okay, to find formulas that relate things together. But you may also be in situations where you're trying to predict what's going to happen in the future, and it'd be nice to have some way of doing that, which is sort of what these distributions are for. So if you're in a particular situation, what can you expect to happen in those situations? What are all the possibilities and how likely they are? That's what this is all about. A distribution is the description of all the possibilities and how likely each one is. Okay? And what we have is that some distributions you just have a list. You just say, here are the possibilities and here are the probabilities that go with them. That's a perfectly good way of describing a distribution. But there are several of them, 6 by the look of it, that have a name. And if someone says, what's the distribution of this? In order to answer the question of what are the possibilities and how likely is everything, you can just say, it's a Poisson with this, parameter of mu. And they'll go, oh yeah, cool, that's everything I need to know. All right, if you were talking to a statistician, obviously. Everyone else would go, what the hell are you talking about? So that is what this is about. So we're going to go through each of them, and the ones that are most confusing to most people are these. The Poisson and the exponential. The binomial often gets a bit confusing to people. But most of you saw the normal distribution at some point in your past at school. Okay, and you waxed lyrical and you found your teacher waxed lyrical about it and you found z-scores and you drew lovely humps. And so you're more familiar with that than with everything else. But for these, the Poisson and the exponential, that's mostly new to people unless you did the IB. In which case you would have seen it already as well. But of course, that was quite some time ago, so you've probably forgotten it anyway. So here we go. I recommend with this in your study to take that list and make it better, and to get each distribution and write down everything you can think about it that goes with it. Okay? So let me do the binomial first. You need something that tells you how to know if you're in a binomial situation. Okay? It's not enough for you to just write down the formula for it or any of those things. You have to actually be able to read the block of text and go, binomial, all right, straight away without having to think about it too much. So a binomial variable is a number, okay? And what it does is it counts how many times something happens, okay? But what it does is if you get a collection of objects, it counts how many of them are of one type compared to another. That's really what it does. So it counts how many times something happens out of a group, basically. So the situations are like how many machine parts are more than 20 millimeters wide, something like that. So we've got out of 20, okay? So there's a fixed amount of objects that you're looking at, and you want to count how many of them are of a particular type. All right? That's roughly what it's going to be like. Or how many light bulbs last under 500 hours out of 100. Okay, that sort of thing, that's what the binomial distribution is measuring. So if you can keep that in your head, it records a count. You're not measuring anything, you're counting how many times something happens, and it's really you're counting how many objects belong in a particular category. Okay? Because the Poisson also counts things as well. So the binomial is counting how many objects are in a particular category. Okay? And it's always out of a fixed number. See, it's like out of 20, it's out of 100 light bulbs. Okay? So, and that condition could just be how many of them are good or bad, and often it's to do with a measurement because they'll combine it into some other question, okay? Because they've only got 4 questions and they have to try and cram as much in there as they can. So that's what the binomial distribution is about. It's counting, that's the most important thing, and it's out of a group, that's the second most important thing, okay? Cool. So being a counted thing, it can only have whole number answers. So that's another way of dealing with it. You say, is it possible for me to have 2.5? No. Okay, so it's not going to be any of the measured things. And so the fact that it's a count is telling you that it's discrete. It's a discrete variable because it's counted as opposed to measured on some sort of scale. Okay? And you have this function that tells you what the probability of every single option is. Okay, so because it's discrete, that means that every particular option for what it could be, every possibility or option, has its own probability, has a probability to go with it. And the list of what probability goes with which option is the probability mass function. Okay? Probability mass function. And it tells you how much probability is there at each option. Okay? And there's usually a formula that tells you what every option, what probability it is based on what the option is. And for the binomial variable, the PMF is the probability of x is n choose x times distressingly pi to the x 1 minus pi to the n minus x. Now all of these things go together. We need to know, so there are 2 unknowns in this formula. We chose x, so we want to know the probability of getting 3 light bulbs in our list. So that's the x. N is how many it's out of. So n is, sort of the out of. And pi is the chances for one object of that occurring. Probability for one object. Okay? Okay, so n is how much it's out of, and pi is the probability for a single object. Right. So, and just as a proper example, I'll get to a proper example in a minute, but it might say, you know, the chances for one light bulb of dying in 500 years is 20%, and so you'll say that that pi there would be 20%, so 0.2. And that n was out of 20, out of 100 light bulbs before. Okay? So you need to know what goes in these spots to figure that out. And notice that this tells you the exact probability of one number x. If you want to know what it is for several of them, you're going to need to do the cumulative mass function. So let's just see, how do we figure out this in MATLAB? What's the MATLAB code? I'm sure it's binom something. Does anyone know? Because I don't know what it is. Let's look it up. Don't you just like binom PDF or something? With a small b, I'm imagining. Binom PDF. And you'd put in the x first, would you? Or the n and the pi first? You need to look that up, because I don't know anything about MATLAB, right? So that's what you need to look up. But you'll have like some commas here, and it will tell you what goes in those spots. All right? And that's the sort of thing that you would put on here. Has anyone got a definitive answer for that? Of what order those numbers go in? I'm just going to see if I can find it, because they all should be roughly the same shape. Binom PDF, so you do the x first, and then the n, and then the pi, according to your notes. All right. However, there's also this thing called the cumulative distribution function. The CDF is cumulative, and it adds it up from one end. So the pictures that's going on here is that you've got a probability for each possible x. All right? And what this is doing is the probability that your binomial variable is like less than or equal to, say, 4. Okay, that sort of thing. That's what the CDF does. And it's really important to consider that equal to, because there is a probability associated with every single number of its own. So less than or equal to 4 is different to less than 4 because it's actually not possible to be equal to 3.5 or 3.9. So this would be like, they start from 0 usually, don't they? 0, something like that. That would be adding up all of these probabilities, everything including 4. Okay, so this would be binom CDF for n pi, right? But if you wanted to know what it was to be exactly less than 4, think about the fact that you can't actually get anything between 3 and 4, so this is really the same as being less than or equal to 3, because it's not possible to be anything between 3 and 4. Okay, whoops, sorry. And that's an important distinction, and you need to remember that if you're working with something that can only be whole numbers, then that's going to happen. This will not happen if it is possible to be anything between 3 and 4. So if it's possible to be 3.99999, then less than 4 is the same as less than or equal to 4, okay? Because you can go all the way up to 999999999, okay? Cool, that's binomial, and that's pretty much everything you want to do, and you just want to know what situation you're in. But I should point out that at this stage, this is when I would say that this happens, the binomial can happen in every other possible situation. You can always turn any situation into a binomial situation. So it's worth noting that sometimes it will happen with something that's normally distributed. So it might be, you'll see it in other situations. You might have something where one variable is normally distributed. So as an example, weight is normally distributed. That twiddle means is distributed as. Is normally distributed with like mean 5 and standard deviation 2 or something. And then it might say, number of objects out of 10 with weight above 3, something like that. And that would be binomially distributed. Okay? It would be out of 10, and we would have to find what probability goes here from the normal distribution. So that information and that information together would tell you what's in this spot. And you would need to know how that's done to know that for a single object, how do I figure out how likely it is for it to be more than 3? Okay? So this is going to happen with the binomial all over the place.
I don't think there's any M in that code. It's just binary.
Sorry?
I don't think it's in the. I think it's just.
Oh, it's bino. You're right. It's just bino for some reason. I'm thinking of a different program. That's really important, isn't it? I don't know whether they'll notice, but worth pointing out. Because if you type binome into MATLAB, it won't know what to do. You're right, it is. In the notes, it just says bino. Okay, that's the binomial distribution. The two other most confusing ones are the Poisson and the exponential because they happen in the same situation. The Poisson, named after Poisson, it counts how many times something happens in time or space. Okay, in time or space. So the other one was out of a group of objects and you count how many of those objects. This one you're counting how many times something happens in time or space. And so you watch and see, you just watch over a certain amount of time and go, it happens here, 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 and here. Okay? And the main difference is that binomial can only have a maximum, like if you're out of 20, binomial can only be 20 at maximum. You can't get any more than that. But Poisson can be as high as you like. Okay? So, note. It can take as high an answer as you like. Okay? Cool. It can take as high an answer as you like, but of course the higher the bigger number, the lower the probability. It's much less likely to see 200 of something than it is to see 20 of something in a certain amount of time. Okay? And we have a PDF, so as an example you might have with the machine part, with the light bulbs, you might say you've got a large number of light bulbs in 500 hours. How many light bulbs will fail? That's the idea. Or it might be something more like, in 2 kilometers of wire, how many faults will appear? Okay, so it can be in space and length as well. It doesn't have to be in time, or it might be, in 12 hours, how many customers will arrive at the shop. Okay, so since it says how many customers, how many faults, how many light bulbs, that's counting a whole number of objects, and that's the most important part. And then you look to see, what is it counting out of? Is it counting out of a fixed number of objects, or is it counting out of a time or space? If it's out of a fixed number of objects, it's binomial. If it's out of time or space, it's Poisson. And it has a PDF as well, which is written in your notes. And it's all based on this parameter mu, which they're calling it. So it doesn't have a PMF anymore, because, oh no, it does have it's a PMF. Because it does have a PMF, because each number has its own probability. The probabilities get smaller as you go up, but they have their own probabilities, and it's like this. The probability of an x is e to the minus mu times mu to the power of x on x factorial. Yay. And that mu is the average number that you would see in that time. So that's the average number that you would see in a particular time or space period. Okay? And that's the most important thing, because they may not tell you what that average is to begin with. Because they will say something like, there's this process, and on average you'll see 1 per hour, and then it'll ask, how many would you see in 12 hours on average? Or what's the probability of seeing 6 in 12 hours? Well, if you see 1 per hour, that mu is actually 12, because you've got 12 hours. That's really important. Okay, and let's just see what it says about Poisson in your notes. No, it uses the mu. So that's Poisson PDF x mu. So it looks like MATLAB likes to put the number first, and then anything else that describes the distribution you're in. So with the binomial, you put the x first, and then you put the n and the pi. And the Poisson, you put the x first, and then you put the mu. And it really is 2 s's, so that's good. And this would have a CDF as well, but there's no decent formula for it. Yeah. Now, it's worth pointing out that this is still one of those situations where less than or equal to is different to less than. So, note the probability that like x is less than or equal to 4 is the same as the probability, strictly less than 4 is the same as the probability that it's less than or equal to 3. That's one of these things, and it's worth kind of remembering that for each distribution, which one it is. And it's because it counts only whole numbers. Okay, it's counting things, so that's good. Okay, so if it was saying how likely is it to have less than 4 faults in your 10 meters of wire, you can calculate it with this with this Poisson CDF. The most important one is the 0 faults, okay, or the 0 customers, or the 0 light bulbs breaking, okay, that sort of thing, because that's actually can be calculated using this formula very easily, because the x is 0, so it's just e to the minus mu. Okay, now what does that leave? That leaves the exponential. The exponential distribution is now a measurement. It measures time or space between events, or until an event happens for the first time. Okay? So I write the word measures because that means it's a continuous. So it's a continuous distribution. The other ones were discrete because they counted. This is continuous because it measures. And in the Poisson, you take a fixed amount of time and you count how many times something happens. The exponential is the other way around. You actually take an event and you measure how far apart they are. Okay? So they're the same situation. So the idea is that here is the beginning of time. Time equals 0. And you might have an event here. Like that. The Poisson is counting how many of them they are. And the exponential is counting how much space there is between them. Okay? A separate exponential distribution for the space between each one of them. Okay. So exponential measures. That's bad. Let's rub it out. Okay, or it could be length. Okay, that's fine as well. Or volume, if you, or whatever. Okay. So, this time, continuous distributions don't have nearly as nice a concept for how to calculate their probabilities. Because since any number is possible, you can have 3.146999497 seconds. Any one amount of seconds doesn't really have a probability of its own. You've only got a description of how likely it is to be near that spot as opposed to being exactly that spot. And so you get this thing, instead of having a thing with boxes, you've got this thing that is nice and smooth. Okay? And it's not possible to figure out, like, the height of this here doesn't tell you anything. It just tells you that it's more likely to be near here than it is here. Whereas in the other one, the height of that box told you the actual probability of being in that spot because it was a box as opposed to just a line. So we want to talk about areas, and so for continuous distributions, the CDF is the most important thing. And I note that on your formula sheet, he does not tell you what the CDF is. And that's really important. Okay? So, I'm going to write the CDF down first. Okay, the CDF tells you the probability from here downwards, so something like that. And that would be my x there. So you would actually go, let's see if I've got this right. That's normal exp. So in MATLAB it's exp PDF. And you put in your number x and you put in the average. Okay, this number mu. And we need to know what that number mu is. That's still the average number. Let's just see what that mu is. Yeah. So that mu is the mean that you would expect to get. Okay. So in 1 unit of time. Okay. So if you would expect 1,000 per hour, it would be 1,000, I think. Let me just see if that's right. Lambda is 1 in 1,000, so that's how many? I just want to read that. Lambda is a rate, isn't it? It's events per time, 1 in every 1,000 hours. Okay. So if the event happens once every 1,000 hours, that mu is 1,000 hours, because that's how long it takes on average for one thing to happen. Okay? So average time to the event. But in your notes, this is actually 1 over lambda. So in your thing, it says that the parameter is lambda, but MATLAB needs you to put in 1 over lambda in this spot here. Okay? That's a very important thing to write down somewhere. Okay, and when it says the exponential distribution with lambda, the mean is 1 over lambda. Okay, so the lambda is how many events happen in a certain amount of time. The lambda is how many events happen in a certain amount of time. But of course, the exponential actually measures time, so it should be the other way around. It should be time per event as opposed to event per time. So this lambda, that there is events per time, like per time, and this here is time per event, or space. Sorry. This mu is time per event, and that lambda is events per time. So, worth pointing that out. Cool, and there's actually a formula for the CDF, which your notes tell you, but your formula sheet does not. And this is the most critical thing that's missing from your formula sheet that I would write down at this time. The PDF, so the CDF, so the probability that x is less than a particular number is 1 minus e to the minus lambda x. So remember that lambda is events per time. Okay, that's the CDF. And that means that the probability, so that's this side there. If you want to know greater than, it will of course be e to the minus lambda x. Okay? Or equal to, it doesn't matter. Remember that for continuous distributions, less than or equal to doesn't make any difference between less than. Okay, because it's possible to go all the way up to 0.999999999. Okay, this is what was used in the example in your lecture notes, which is here. I'll give you time to keep still writing. This example is page 33. It says, suppose the lifetime t of a bulb is exponentially distributed with lambda is 1 in 1,000. So that's one light bulb death for every 1,000 hours. Find the probability that a randomly chosen bulb will last for at least 800 hours. So t is exponential with lambda is 1 over 1,000. That's the way of writing it. So capital F of t, that's the CDF there, which is the probability that's less than or equal to t. It's 1 minus e to the minus lambda t. He just wrote down the fact. And then he said, well, to be greater than a particular time would be e to the minus lambda t. And then so to be greater than y5, oh, that's a typo. To be greater than 800, it will be e to the minus 1 over 1,000 times 800, which is what this number here is. And so you just sub that in and that's the probability. But with MATLAB, you can, of course, just type XCDF. Right. So back here, it appears that when I do this wide, that's a C here, because it's obviously a CDF, not a PDF. It will tell you PDF as well, but all that tells you is the height of the curve, and nobody cares, okay, unless you want to get MATLAB to draw the curve for you. All right, so the key there is to know what is being measured at any given moment. So he gave an example, I'm sure, in his example thing here. So what are we looking at here? No, that's the wrong question. A random variables question. The tensile strength samples of paper from a certain mill can be modeled by a normal distribution. Okay, so that doesn't use the exponential. Have we got another one? We so don't. Okay, I'm just going to... But I want to show you something. Hopefully you know how to do normal distributions, and I'm not going to do it now because we've already gone 20 minutes into the next hour and I just don't really feel like doing this much longer. And I want to give you some chances to ask questions. But you see here, this is a normal distribution question. So this part here is all about a single object, and you're measuring how strong it is. And so you've got a measurement of one object, okay? So that's the continuous one, which is the normal. This one here, we've got 25 samples of paper, and X is how many have a tensile strength greater than 32 psi. So I'm counting out of 25 samples how many of them are for certain categories, so that's binomial. So if I were to state the distribution, with a sharper pencil, that would be binomial, just B, I reckon, binomial with 25, and there'll be a probability in this bit, which would be the answer from part 1, because part 1 was finding out how likely it is to be more than 32. So we get the answer from part 1 and we'll put it in there. And now we've got a brand new question and we can ignore part 1 from now and do this question here. And you'll note that it says find the mean and standard deviation of x. Well, that's what is on your formula sheet. See? Mean and variance. But note that the standard deviation is the square root of that. Okay? So I would recommend that you do that for each of your variables. For uniform, for exponential, for normal, for Poisson. Some of them have formulas for how to calculate them. Some of them you can only do using a computer, like the normal distribution. And that would help you with those things. Right. So, any questions of any kind now? About anything, even if I haven't talked about it yet? Yep?
With binomial distribution, using that formula, how do you actually go about using the formula?
I will do that now. But I'm going to guess, just not going to answer that previous, I might as well answer that previous question. So, I've just been asked, with binomial, how do you go about using the binomial formula? So let me go back to my sheet where I was talking about binomial. So I was here, so this formula just here? Okay, so let's do an example. So suppose you've got probability that one of my students leaves during the lecture is 20%. Okay? Is 0.2. And so, out of 150 students in the lecture, what's the probability that half of them leave, right? That sort of thing, okay? So we know it's a binomial situation because I've got 150 students and I'm counting how many of them are in a certain category, I'm counting how many of them leave, and I know that's binomial. So I've got, if x is the number that leave, x is distributed as a binomial with 150 and a probability of 0.2. Okay, so this is my n, and that's my pi. All right, I can sub them into the formula in this way, and what I'm looking for is what's the probability of it coming out to 75. Okay, because I want to know what's the probability that 75 of them leave. So, according to the formula, it will be 150 choose 75 times 0.2 to the 75 times 0.8 to the 75. But can I change it to 70 because it will be more illustrative that way? So if it was 70, these two numbers here add up to 1. So this is the pi, and this is the 1 minus pi. Okay? And these two numbers here add up to the 150. Okay? So this is the x, and this is the n minus x. So I actually never remember the formula. I just remember the probability to the power of 70, because there's 70 students and it's 0.2 of them leaving. And then it's the rest of the probability to the rest of the students. Okay? And then you would put that in the calculator of some sort. So most calculators actually have an NCR somewhere. So who has a Casio? Do you know where it is in the Casio?
In the stats part.
Yeah. So in a Casio you'll go options, It's in the stats, isn't it? Oh, in the Casio, you can actually just go to the stats task and ask it what probability x equals 70 is. Okay, and you should be able to do that in a TI somewhere. If you don't have a calculator with you, or your graphics calculator dies during the exam and you need to do something by hand, and this one will be impossible by hand, but if you had to do it, an ordinary calculator, the button that does that is called NCR. To do this bit here. Okay, so to get that, you would go 150 NCR 70, and it would produce the answer. In a Texas Instruments, you can only find the NCR by looking in the catalogue. In a Casio, you go options, prob, and it's there. And on an ordinary scientific calculator, NCR should be somewhere on the buttons somewhere. It's probably shift plus, something like that. It's shift one of the other things. So if you ever need to calculate that, go for it. But useful numbers are that choose 0 is always 1. And so like n choose 0 is always 1, and n choose n is always 1, and n choose 1 is always n. So that means you can shortcut it. So if I want to know what's the probability that one student leaves, it would be 150 in that spot instead of 150 choose 1. Okay? So just as another example, the probability that x is equal to 1 would be 150 choose 1 times 0.2 to the 1 times 0.8 to the 149. And 150 choose 1 is just 150. If you're ever interested in how that works. There are other formulas for how to calculate NCR, but you should find out where it is in your calculator to do it directly, because you just don't have that much time, and you probably prefer to focus on something else. Okay, but for the less than or equal to's, it's safest that Gary probably won't ask, because you'd need a graphics calculator to do that, unless you just separately added them all up. So if you want to know less than or equal to 4, you could do 0 and 1 and 2 and 3 and 4 separately and add them all up. Okay? So don't forget that 0 is actually one of the options. It doesn't start at 1. It's possible for none of the students to leave. Right? So, yeah, don't forget that. Feel free to start going if you want to, but I'm going to keep answering questions until 12 if people are interested. So, anyone got any more questions? Yep? Oh, okay. So I've got a question about p-values and t's. Yeah? Which is probably what that graph will do. So, all hypothesis tests run the same way. I'll just give people a chance to leave if they're going to, and then start answering that question. Okay, so p-values belong to hypothesis tests, which is what Gary is calling inference. Okay, so all hypothesis tests concern having some sort of null hypothesis which would be like the H0 equal, something. And that null hypothesis is always about things being equal or things being the same or there being no relationship. It's all about nothing. Okay, so that's why it's called null. So in regression, the null hypothesis is that there is no relationship. In a t-test, the null hypothesis is that there is no difference. And in the binomial situation where you're counting how many times things happen, your question is that it's not different to what you think it is. If there's two different proportions, the null hypothesis is that there is no difference in those proportions, okay? There are some versions of stats where that is not true, but everything that you are taught, it is nothing, the null hypothesis. And the idea is that you assume that the null hypothesis is true and do various mathematical calculations using your data based on that assumption to produce a p-value. So the idea is that assume the null hypothesis is true, and then you do calculations with the data to produce a test statistic. And the reason you do that is that you actually want to know how surprised you should be to get the data you have if in fact the null hypothesis is true. So in a t-test where you're comparing two groups, you would like to say, if in fact, on average, this group is the same as this group, you know that some of these are going to be different to some of these, but if on average the averages are the same, how likely is it to see the data that I see? Should I be surprised at seeing this if in fact there's no difference? That's what I'm talking about. Okay? So if I find that the average in this is 5 and the average in this is 200, how surprised should I be at that happening? If in fact that for all of them the difference of the averages are the same. Okay? Or if the average in this group is 5 and the average of this group is 6, how surprised should I be? That's what the p-value represents. And so you have to calculate a test statistic that says, instead of going based on my averages, now I can convert that all into a t, so it might be a t, or it might be a z, or it might be... No, that's pretty much everything you've been told. But for other hypothesis tests, it might be a chi-squared, or it might be an f, or it might be something else entirely. And from that, you decide, instead of saying, looking at my whole list of data, how surprised should I be? I look at just that number and say, my t came out as 8. How surprised should I be? Because if the null hypothesis was true, on average, t should come out to 0. Okay, that's what the t is representing. A t of 0 represents no difference at all in your sample. Okay, and a z of 0 represents no difference. So 0, value equals 0 represents no difference in my sample. And so the bigger it is, the more surprised I am, because I'm all working under the assumption that there is no difference. And so if there's no difference, it comes out as 0.5, I go, oh yeah, that's not too bad. And so I conclude that 0, maybe there isn't a difference. But the bigger that number gets, the more surprised I am that this happened if there's no difference. You say, if there was no difference, I've got a t of 16. That's almost impossible if there's no difference, and so I conclude that there is a difference after all. Okay? So the bigger this gets, the further from the null hypothesis you are. That's what that means. And a better way of dealing with that is to convert it all to p-values. And so from here, so we've got the value of that, and a big value represents far from the null hypothesis. Okay? So a value of 0 represents close to what the null hypothesis would normally produce, and a big value represents far from what the null hypothesis would normally produce. And so you use that to calculate a p-value, which is literally the probability of getting a number that big, okay, or bigger. And so once you've got a p-value, this time it's the other way around. A value of 0 indicates that this is impossible if the null hypothesis is true. Okay? So p-value of 0 indicates my data is that this value of t is impossible if the null hypothesis is true, which means that the null hypothesis can't be true because the t happened. Okay? So what that means is impossible if h0 is true, so we conclude that h0 is not true. Okay, that's the idea. Whereas a p-value of 1 means that this always happens if the null hypothesis is true. And so we conclude that the null hypothesis is in fact true, because if it was, this would happen every time. Okay? So, and there's grades between there. And so if the p-value is small, it means that you've got less faith in your null hypothesis, and the p-value is big, you've got greater faith in your null hypothesis. A p-value is in a way, you will never write this in an exam, but it's a measure of your faith in the null hypothesis. Okay, so low p equals low faith in the null hypothesis. Okay, but you'll never say that, right? Because that's just like statisticians will slap you if you say something like that. But that's what it means. And so you usually choose a cutoff point to decide whether it is low or high. And so the cutoff point is traditionally 0.05, but Gary will tell you what it is. If he doesn't tell you, it will be obvious. Okay, so if he doesn't tell you which way to do it, he doesn't say at the 5% significance level. What that means is that's the cutoff when you say it's low. So the significance level is the cutoff for a low p-value. Okay. So if he doesn't tell you, it'll be obvious. I suppose he says, you know, in this hypothesis, what do you test, what do you conclude? And going, you haven't told me the significance level, but then you look at the p-value and it's 0.000007 and you go, well, that's just obvious, right? Or it comes out to 0.73, which is shockingly huge. And no matter whether you pick 0.05 or 0.01 or 0.10 or 0.10, it wouldn't matter. You would still say that the null hypothesis is true. Though technically you're not allowed to say null hypothesis is true, you just say retain the null hypothesis. Okay, that's how it works. So it's just good to know that a bigger t or a bigger z gives you a lower p-value and therefore less faith in the null hypothesis. So having a look at this, this does not tell you the test statistic, right? This is telling you the estimate and the standard error. To get the test statistic, you will go this divided by that. Okay? So divide here, those two, divide them to get the test statistic. All right? And then it will be, we'll use a z in this case. Every time it's a normal distribution, that's actually a z. I don't know why. I think because n actually usually represents the sample size, so you've already used n, and it's probably German. Or maybe it's an n on its side, but whatever. Z stands for the normal distribution. And so that's where you'll look it up. You'll calculate this number, and then you'll look that up on some sort of distribution. So as a proper example, we might have like, you know, want to know if the mean of the weight of some object is 300 grams, right? And so we take a sample of maybe 50 and we calculate the mean of, say, 290 grams and the standard deviation and a standard deviation of 20. All right, so like that, and then you would say, you know, perform a hypothesis test. Do a hypothesis test to answer the question. Okay, so that's sort of what you would do. So you'd write your null hypothesis, which is that the mean is 300. And then your alternative one would be that it's not 300. I don't know if Gary asks you to do alternatives, does he? Does he care? Probably doesn't matter. and then you'll calculate your test statistic. And according to this table here, now what have we got where the context is a normal distribution with a mean? We just assume it's a normal distribution. I should have said that, but I'm going to skip that bit. If you've got a large enough sample size, it doesn't matter. So a normal distribution, and I don't know what the true standard deviation is because nowhere does it mention what the standard deviation of weight is before I even start. I have to use the sample standard deviation. So if I have to use the sample standard deviation, that means I'm in this situation here. Okay? So if he doesn't tell you the population standard deviation is this number, then it's this situation here. Okay, so this says I should use x bar and s on root n. Okay? So t is x bar divided by s on root n. And so x bar would mean the sample mean, which was 290. I need to compare it to the 300. I actually have to subtract the mean. So I have a feeling that we have to actually, first we have to subtract these and then divide. So x bar minus mu divided by that. X1 minus x bar minus that divided by that, okay? So we subtract these, this minus that divided by that. That's how to make the hypothesis test, okay? So x bar minus mu divided by that, so x bar was 290, mu was 300, s was 20, and n was 50, and I do that calculation, and it comes out to an answer. Would someone mind? No, I'll just use Excel, unless someone can do it quicker than me. Is it? No, it's all right. 3.54. Okay? Oh, yes, it is a minus, thank you. Because 290 is less than 300. So I've got minus 3.54. And what I would do is I would look that up in the t distribution. So see how it says reference distribution here? And it's t n minus 1. So I will go to the n minus 1th t distribution and I will find out what it is. So I have a feeling that what you will do if you were typing it in MATLAB, you would actually go, let's see, let's draw it. Okay, so you know that list of distributions you had. You've got Poisson, you've got normal, you've got uniform, you've got whatever. There's another distribution called the t distribution. And it never happens in real life. When it happens is when you do this calculation. Okay, and so you mark, the 0 is always in the middle, mine is minus 3.54, and I need to know how unlikely it is to get something that big, that far away from 0, because 0 would be the null hypothesis, right? Because the null hypothesis would be that it's supposed to be 300, so if I put 300 here, that would give me 0. So I want to know how likely it is to be further away from 0 than that, and I would be just as surprised if it was 310. Okay, I'd be just as surprised if it was that far from the mean but on the other side, so I'm going to colour in this as well. Okay, I had the slightest suspicion he may have told you about one-tailed and two-tailed, did he? Good, he shouldn't have, knowing Gary, so we're not going to do that. And we would like to know what that probability is. So notice that this bit here, CDFs give you the bit on the left-hand side, so I could actually ask in MATLAB, T CDF minus 3.54, and what I need to do is the t distribution with n minus 1 degrees of freedom. So this is actually T49. Okay, you know how a normal distribution needs a mean and a standard deviation, and a Poisson distribution needs a lambda. A t distribution needs an n minus 1 or an n minus 2. Okay, so it'll just be like that, and that will give me this number. But of course, I'll need to times it by 2 to get the total amount, and that's the p-value. Yep?
What are the different scenarios where you use t minus 1 and t minus 2?
Yep. N minus 1 is for, yeah, I'll tell you. I'll work my way down. It's in the table here, okay? So that number changes depending on what calculation you have to do to produce the t. And it's usually to do with the calculation that's done to produce this standard deviation. So along the way to produce a standard deviation, you have to divide by an n minus 1 at some point in that calculation. And the reason you have to do that is because you're adding together a whole lot of n numbers, but you've already calculated the mean. So you've lost one piece of information by having to calculate the mean. And so you go down one t distribution. And in regression, you have to calculate the slope and the intercept before you can calculate the t statistic. So you lose two pieces of information. So it's n minus 2. The standard deviation doesn't count. Calculating the mean doesn't count. It's the point at which you calculate a standard deviation that's the issue. If you already knew what the standard deviation was and you didn't have to calculate it from your sample, you actually start at sort of 0 degrees of freedom, which is the normal distribution. You don't. The normal distribution is actually infinitely many degrees of freedom, so it's just don't worry about it. You just have to know, which is why he gave it to you in your table. See here how it says n minus 1 for the t here in this situation. But if I'm comparing two groups to each other, I do n minus 1, but only for the smallest group. That's what this bit here means. So the minimum of the sizes of the two groups, minus 1. So I get the smallest group and I do n minus 1 for that group. If I'm doing a paired, I'll do this. In regression, they're all n minus 2. Okay? If you were doing multiple regression, where your formula had, instead of just one x, it had x1, x2, x3, x4, you'd have to take off how many x's there are. So, which I'm sure you'll get to eventually when you do statistics and engineering or something, if you ever need to do that. So, finally, the big and most difficult part is to know how to decide which of these you want to do in any given situation. And that's based on the type of thing that is recorded for each object in your experiment and how it's been arranged, how the data is arranged. So, do people have trouble telling between a paired and an unpaired t-test? Do you know what I mean by that? Okay. So you'll notice here he's got normal mean, sigma not known, he's got two independent samples and paired comparison. Do you know how to tell whether you're in what situation those belong to? No, okay. Sorry? Or not, yeah. But the key is that in this paired comparison, it's actually only one sample. Okay? One sample, and you've measured everything in that sample twice. Whereas in the other one, you've got two completely separate groups, and you've measured this group once and this group once. Okay, so that's the basic idea. So the difference between these is that this is one group of objects, and you put them under situation A, and another group of objects under situation B, and you've measured them separately. And I like to think of that as people, because I usually do medical statistics. So you've got one group of objects, and they've been measured under two each. This is like situation A and situation B. Okay? Whereas this one here, you've only got one big group, and you measure them under situation A, and you measure them under situation B as well. Okay? So the paired it's this way. That one's there, and that one's there. So the paired comparisons, these are your objects that you're measuring, and you put them under both situations. So you might be maybe treating metal or something, and you've got, that won't work. In this situation, you might be treating metal to try and find its strength, and you've got one block of metal bars that you treat under treatment A and another block under treatment B, and you measure them both. But this one would be that every block has actually been put under both treatments. Maybe one end of the block is done on one treatment, the other's on another treatment, and they belong to the same object. Or if you're doing maybe water engineering, it might be that you've got two measurements in the same year, which is what this would be. This would be a year, and you've got a measurement in summer and a measurement in winter, and they're actually compared to each other. Whereas in this one, you've got like from from 1990 to 2000 you've only got winter, and from 2000 to 2010 you've only got summer. So they're completely separate groups. So it depends on how many measurements are made on each object. This one, each object has 2, and in this one, each object only has 1 measurement. So yeah, I like my picture. It works much better for medicine than it does for engineering. And all the other ones, you don't have to worry about that because you're not put in that situation. So, and this binomial thing is actually saying that each object, the thing that you have written down is a yes or no. Okay, so in this one, the thing you've written down about each object under study is a number. Okay, there's numerical, quantitative variables written down. Whereas this one, the number that you write down is actually for the whole group at once. You count how many times something happens in your group, but for each object in the group, it's just yes or no. So the decision is based on what's happening for each object. And in regression, you have 2 completely separate measurements on everything. It's not the same measurement twice under 2 different situations. It's measurement A and measurement B, depth and cost, or height and length, or something like that. Okay? So they're the most important things. Regression is usually fairly obvious because there's a scatter plot there somewhere. But the other ones, it's important to know what information you've got. And so this here is about comparing one proportion, so a percentage, to a particular answer. Whereas, so this is, here is compared to a particular answer. This is compared 2 situations to each other. This is compared to a particular answer. These are comparing 2 situations. Okay? And notice that this one is for the hypothesis test, and this one is for the confidence interval. So it's important to separate those on your chart, because the formula that you use in this proportion situation for the hypothesis test is different to the confidence interval. So just to let you know, we have our estimate minus parameter divided by standard error. That's the hypothesis test. For a confidence interval, we take the estimate plus or minus the t or z times the standard error. And so you use the same information in the table in a different order. So these are the titles of these columns here. Okay? So, for example, in this situation, here with the binomial test, it'll be estimate minus parameter divided by standard error, and that's a z. Okay? But for the confidence interval, it will be estimate plus or minus z times that parameter. And you choose the z or the t in this formula here to be the one that would give you 0.05 or 0.0 whatever in the hypothesis test. So if this has got 5% significance level, this would be a 95% confidence interval, and that t would give you the 5% if it was a hypothesis test. So with a Z1, it'll be 1.96 for a 95% confidence interval. Whereas over here, if you did a Z, it would come out to whatever answer it comes out to you to, and you would look it up and it would tell you the probability. But if the answer came out to exactly 1.96, the p-value would be 5%, and you need to choose that number in the confidence interval here. All right, there's only 5 minutes left. I can probably do one more question if someone wants to ask. Or not.
Do you have any tips on how to study for the MATLAB readout?
Well, let's base this on my experience about 2 hours ago of looking at the MATLAB readout to begin with and having utterly no clue what to do. I think practice. I would actually practice typing things into MATLAB. So you know what MATLAB readout is supposed to look like. So the first tip is to not be freaked out by the times and the brackets and whatever. If it's for statistics, you do want to just know in your head what you would type in and what answer it will produce and which of those things are the p-value and which of those things are those things. And I don't really know how to study those things, but you can line them all up on a piece of paper for yourself. This code produces this answer and gives you, and this is where the information is that I'm looking for. And did you do pracs or something? You did like in a computer room with MATLAB? Really?
Some of our assignments were on MATLAB.
Okay, so if you did some assignments on MATLAB, it'd be worth going back to that and seeing what things were typed in those assignments to produce what output, because he will base his MATLAB stuff on what he did in the assignments, because otherwise that would be totally unfair, and Gary is in general a very reasonable person. So I would use, but focus particularly on, because what he's going to want you to do if he wants to read output is, because you had all this output and then he said, like, you know, what's the p-value? And so you need to know where in the output the p-value is supposed to appear, even if it's in a different order. So think about what typing would produce what, and how it matches with your other knowledge of MATLAB. So he had like a square bracket there with commas between it, and all that's doing is making a matrix, right? And so think about what you know about how MATLAB works normally. And so when there's an equals, it means he's just assigning something to a variable. And so when he says m1 equals whatever, that means he's just doing a calculation. And so you can compare it to what you would do by hand and saying which bit of the code matches with which bit that I would do by hand. And that's probably something else I would recommend. And that's what I would do for all courses of any kind where there's computer output involved. Usually it matches with something that you could possibly do by hand given enough time. And there'd be some theory that goes to how it would be done in the calculation, and that's fed into the computer, and I would line them up. So if you ever do any more computer science sorts of things, or simulations or numerical analysis or whatever, most things match with some sort of theory that can be written down by hand, and it's line them up next to each other so that you can remember both at the same time, because then you don't have to remember the code separately from the theory. You've got them both in the same place in your brain, so they're easier to find. Yeah. Cool. It's probably time to stop, unless there's anything else. Yep?
The maths drop-in centre, is that for first years or is that for first years?
The maths drop-in centre is for first years pretty much. Well, I will help first years before you. So the closer we get to the exam, which is your exam's on the same day as the first year maths exams, so the closer we get to that exam, the less room there will be for you. But feel free to use the space next door, right, and study together. I would recommend that, look, to kind of try your best not to use us because you can't use us in the exam. But you can clarify some of these things. So if you're going through your exam and you're going, I've got these solutions, I've got the questions, what the hell happened there? That's a perfectly good question to ask the Maths Learning Centre because we can try and figure it out with you. But I'd really recommend trying to do it for yourself because the further you go into your degree, the less time I will have for you because I think you should have figured this out by now. But the statistics, I have compassion for you because statistics is very difficult for most people, and most people who are good at maths are afraid of stats in the same way that ordinary people are afraid of maths. So you can come and talk to me about something that I've said today or that sort of thing, but just warn you that I will help first years first. So that's one of the reasons I did this, so that I could get you all together in one go and say, here's a whole lot of stuff, and you can ask me some questions now. Yeah. But if you have any more, do come, but know that most of my staff aren't all that good at this anyway. I'm the only one who really knows pretty much anything about stats, and I only did the end of second year stats. And the differential equations, well, I don't know much about that at all. We've only got a couple of staff that know about it already, in that sense that can just look at it and know what's going on already. So I would really recommend that you bug your lecturers as much as you possibly can. Because they need to know what you're finding difficult now so that next year's students can be better off and so that they can maybe tell, say, the Engineering Maths 2 lecturer, everyone really struggled with this, maybe you can be a bit more gentle on them in that area. They might not listen, but it's worth a try. Yeah, that's the long answer. The short answer is sort of no. But I did this anyway. This is my last-ditch effort to help you guys before I hope that you can fly on your own. Most people don't come for Engineering Maths 2, and so I assume that means that it's not as bad. But if you just for now, I'm going to say it now before I forget, I'll try and come to your first lecture. If you have to do Engineering Maths 2, you're going to need to know how to do partial fractions from Maths 1A, from integration, because you're going to be doing Fourier series. And you're going to need to know quite a bit of complex, be familiar with your complex numbers. So I will attempt to get some resources into the MyUni course for Engineering Maths 2 between now and when it starts, so that if you feel like brushing up on that at the time that it comes, you'll be able to access it at the time. So, but techniques of integration is really important because you're still doing differential equations, especially partial fractions, and so are complex numbers. So just my warning for Engineering Maths 2. But please feel free to forget that until after your exam, and then I'll put something in the Engineering Maths 2 website to try and help give some resources to brush up on those at the time you need to. You can always come to the Maths Learning Centre to try and revise first year, okay? Yep?
Do they have integration of G6? I'm not going to see more for example.
Sorry?
Do they have integration to start with the Maths Learning Centre?
Yep, so in the Maths Learning Centre I've got all the resources I made for Maths 1A. So I've got that great big book of integration examples, and I've got the list of different integration techniques. What I'll do is put the revision video that I had. Do you want that like in your course now? Is that helpful for Maths, Engineering Maths 1, revising integration techniques? Yes?
Does it have integration by parts?
Yes. Okay. I will tell Trent, I'll give Trent a link to the video that I did revising that for the first years and the resources that go with it, so that you can revise your integration. And if I don't write that on my hand, I will forget. I'll write it. So we want integration for EM1. Cool. That will happen at some point in the next couple of days. If it doesn't, email Maths Learning and let me know. You know, you would not believe how many emails I got asking whether we've recorded it. So lesson for the future, always say I'm going to record it in the announcement. Because I had like 50 emails. So cool, this recording will go up as soon as I can. Probably won't be up until Monday. So if anyone is asking you, that's probably what's going to happen. Thanks guys, good luck. Good luck.